Welcome back. So in this video I am going to talk about the notion of frequency, digital frequency. But before that, if you recall, I had asked you about the Fourier transform of un. Okay, the DTFT of un, it turns out, is defined as pi times delta, pi times summation k runs from minus infinity to infinity delta of omega plus 2 pi k plus 1 by 1 minus e power minus j omega. Now you may actually wonder why this is the case. Okay, this can be understood by seeing that we can actually have a reasonable degree of clarity about this particular part whenever omega is not equal to 0 or a multiple of 2 pi. Because when omega is actually 0 or a multiple of 2 pi, then 1 upon 1 minus 1 is undefined. So the 0 case alone has to be handled in a tactful way. So for the 0 case alone, there is some extra stuff over here which results in an impulse. So this is a special case, and one question is, how do you derive this? So it turns out that this can be derived using some careful way. So if you see that this pi times k runs from minus infinity delta of omega plus 2 pi k, this is very related to the DTFT of the all one sequence, because the DTFT of the, or rather the all one sequence has DTFT, all one sequence has DTFT summation k runs from minus infinity to infinity, okay, 2 pi delta of omega plus 2 pi k. Now first let's understand why this is the case. For this I am not going to go into the complete details, but if you think about the all ones, let's say the signal x of t is equal to 1, continuous time. This is the DC sequence. Obviously it's band limited because the only frequency present in it is 0 Hz. So x of t is 0 Hz, it's a continuous time signal. Now if you sample this continuous time signal, what do you get? You will get 1, 1, 1, 1, 1. That's true. But what is the continuous time Fourier transform of this? It is delta of t. Remember this? So if you now look at the continuous the DTFT of this, what is the so if you sample the signal, rather, what happens to the spectrum of the sampled signal? Delta of t repeats, and delta of t will repeat exactly every fs dimensionals. Okay, really. So what is the connection between the DTFT and the continuous time Fourier transform? So that is something which we will see in this video. Let's say you have a band limited signal x of t. That is, it's band limited to have range of values only between minus w and w, let's say. And suppose that we sample it at more than 2w. I'm sorry about this. Okay, let's say we sample this at more than 2w. Okay. Okay, so then you're going to have this and this, and you're going to have another repetition. Okay, let me make it more accurate. Okay, so I'll actually select an object, select this object, and I'll copy, I'll paste. Okay, so let's paste it about here, let's paste it about here, and so on. Okay, and oops, I'm sorry about this. So now this gap, this particular location is fs, this particular location is minus fs. Okay, so whatever the useful part of the signal is, as we have seen in sampling, is between minus fs by 2 and fs by 2, which now means that if you now want to look at this as a DTFT, it's very simple. All you do is you rename this as minus pi, you rename this as pi, and there's an extra scaling, and that's it. Which means that the DTFT is just the continuous time Fourier transform of the sampled signal, except that the axes are scaled so that the fs corresponds to 2 pi. So fs over here corresponds to 2 pi in the DTFT. So this gives you a direct connection between the continuous time frequency and the discrete time frequency. Really? What does it mean? This means that small omega, let's say, I'll use a black pen. Let's say that small omega is the discrete time frequency and f is the continuous time frequency. 0 corresponds to 0 hertz. Pi corresponds to fs by 2. You can see. And then there's a linear relationship. So if I ask you something like 0.3 pi, that will correspond to 0.3 fs by 2 in hertz. Or if I ask you for omega equal to 1, then it will be fs divided by 2 pi hertz. Just linear scaling, because pi corresponds to fs by 2, 1 corresponds to fs by 2 pi hertz. So this is the relationship between the continuous time and discrete time frequencies if you are considering this discrete time signal to have been obtained by sampling a band limited continuous time signal. So when you want to go back to the continuous time signal, all you need to do is you need to just do the reverse labeling. You basically place a sinc filter here, which is a rect in frequency domain, and that just maps minus pi to fs by minus fs by 2 and pi to fs by 2, and that's it, you're done. So in other words, this is exactly what is happening when you connect. Now let's go back to when you connect the discrete time and continuous time. Now let's go back to our xn is equal to 1. The xn is equal to 1 corresponds to x of t being so x of t being the DC, and then so for let's say the x of t is equal to 1, that means its Fourier transform will be this impulse. So what happens when you sample the signal? This impulse gets repeated every 2 pi, and then you just have to scale it by 2 pi, of course. And then what about the x-axis? Minus fs by 2 becomes minus pi, plus fs by 2 becomes plus pi, and therefore this DTFT definition makes sense. Okay. Similarly, if you go through a similar argument for u of t, you will get this back. Okay. So implicitly, we have also mentioned one thing. The principal branch of this DTFT is between minus pi and pi, which means that pi is the highest frequency in discrete time. What does that mean? Pi being the highest frequency. So pi being the highest frequency has a special meaning. If you take the sequence, let's say you take the sequence minus 1 power n. That sequence is very easy to draw. It's 1 minus 1, 1 minus 1, 1 minus 1. Okay. Notice that it just goes high, low, high, low, high, low successively. So minus 1 power n is the, loosely speaking, fastest varying discrete time sequence or signal. Now you can argue it's not just minus 1 power n, it can be minus a, minus a, or something. It can be minus 0.2, plus 0.2, minus 0.2, plus 0.2. All of those are just scaled versions of minus 1 power n. But minus 1 power n, if you look carefully, is actually e power j pi n. And this, if you read the omega naught, is pi. Any faster movement will actually wrap back. In other words, for example, if you say, oh, I will do e power j not pi n, I'll do e power j 2 pi n. But that's just all one sequence. E power j 1.2 pi n. the same as e power minus j 0.8 pi n. So pi is the and corresponding minus pi is the highest frequency that you can represent in the DC case. So unlike continuous time, there is a notion of the fastest varying signal which just alternates. So there's nothing more you can do. Okay, this is the maximum frequency that is present. This is also a side effect of the fact that you have sampled the signal. When you sampled, you have restricted the frequency range to being between minus fs by 2 and fs by 2. Automatically, by doing that, you are restricting the digital frequency also to be between minus pi and pi. Notice that the maths also translates elegantly. The periodicity is captured in the fact that you are representing the DTFT directly as something like x of e power j omega n. So here the periodicity is captured naturally. So to that extent, digital frequencies are always between minus pi and pi. Digital frequencies are always between these. Of course, you can always say 3 pi, but that just means the same as pi. Okay. So always remember, discrete digital frequencies are limited. The reason is because you're sampled and you've already said that I cannot take any sequences to the left of minus fs by 2 to the right of fs by 2. Okay. Thank you.